point was. Okay, so you wouldn't have to, well, it wouldn't be titrations without calculations. So we're going to look through some of the calculations of titration methods here. So this is just a bit of a reminder, because you would have seen this in year one. So remember, the equivalence point is the point at when neutralization occurs. So a pH meter is really used when you want to plot a graph to show this. So let's look at this example. So we've got 15.7 centimeters cubed of 0.450 moles per dm cubed of sulfuric acid was required to neutralize 0.120 moles per dm cubed of sodium hydroxide. Calculate the volume of sodium hydroxide being neutralized in centimeters cubed. So the first thing is we write out our balanced equation. So this is H2SO4, which is sulfuric acid, reacting with sodium hydroxide, and that will form sodium sulfate and water. You can see here we're going to put sulfuric acid in the burette, sodium hydroxide in the conical flask. Then what we have to do is calculate the number of moles of sulfuric acid. So moles is concentration, that's moles per dm cubed, times by volume. So that's 0.45 times by 15.7 times 10 to the minus 3. So what we've done here is we've got 0.45, which is the concentration, and the volume is 15.7. But what I've done is I've added times 10 to the minus 3 on the side there, because what that does is it shows us, well, by adding that, effectively you're dividing it by 1,000, and that converts centimeters cubed into decimeters cubed. So there we are, okay? So you can just divide that by 1,000 if you want. I find it easier to just put times 10 to the minus 3 on the end of anything that you want to divide by 3, because it just keeps it cleaner. Okay, so the third thing was then we use the equation to find out the molar ratio in order to work out moles of sodium hydroxide, and we call this stoichiometry. So for example, we have a 1:2 ratio between sulfuric acid and sodium hydroxide. So what that means is the number of moles of sodium hydroxide, so which is this bit here, is 2 times the moles of sulfuric acid. So the number of moles of sodium hydroxide is 2 times 7.07 times by 10 to the minus 3, because that's what we've just worked out here. And that's going to give us 0.0141 moles of sodium hydroxide. So basically we're working out that. And then the fourth one, the last step, is we now calculate the volume using volume divided by moles, volume equals moles divided by concentration. And we need to divide that by 1,000 to get centimeters cubed at the end as well. So the volume in decimeters cubed is moles divided by concentration. So the volume is 0.0141 divided by 0.120, because that's the concentration that we've been told, which is here, and that gets us 0.118 decimeters cubed. We need to find it in centimeters cubed because that's what the question's after. So we times it by 1,000 to get centimeters cubed. That should say times by 1,000 rather than divide. Okay. So this is looking at the last section of this topic, which is the introduction to buffers. So a buffer is a chemical that resists the change in pH when small amounts of acid or base are added. It doesn't stop the change, it just resists it, okay? That's really important. Buffers do not stop the change, like we said, and there's 2 types of buffers. We have an acidic buffer and we have a basic buffer, and we need to understand both. Buffers can be quite complicated, so I want you to listen carefully to this element in particular, looking at the mechanics of a buffer and try to explain it in the best way possible. I think the key thing in an exam though with a buffer is being able to articulate yourself, to give a reason why a buffer works, or why, explaining your reasoning. And some of you'll see here the way I describe it in the written part here is to try and get as many keywords in there as possible, and you'll see what I mean. Okay, so acidic buffers. So acidic buffers resist the change in pH in order to keep the solution below pH 7, because acids are pH 7. So that's key. Resist is the key word here. They are made from a weak acid and its salt. Okay, not any salt. It's got to be the salt of the weak acid that you're using. Okay. So an acidic buffer is using ethanoic acid, so that's CH3COOH, which is your weak acid, and sodium ethanoate, which is its salt. Okay, so basically we take that and mix it, and we've got a buffer. Okay, they're really simple to make, but they're really complicated to understand. So, right, in any buffer solution, but I'll try and make it as simple as I can, of course. So in any buffer solution, there are two equilibrium equations at play, okay? So the two equations coexist in the same beaker. So we've got one beaker with two reactions going on at once, okay? So just pause there for a moment. Right, here's the first equation, okay? So equation 1 is the acid, the weak acid, which is dissociating to form the ion and the H+ ion. So we've got large amounts of this acid. Remember, a weak acid dissociates poorly. So we have lots of this and not much of this. So equilibrium is well over to the left. We have a large amount of them acid molecules. The other reaction that's going on in this beaker, remember there's two. The other one is the salt, because we've chucked in a salt into the beaker as well. The salt is dissociating it because it dissolves in water. So it breaks down to form this, in this case it's an ethanoate ion and a sodium ion. But because a salt dissolves really well, we don't have much of the original salt at all. It pretty much breaks down fully into your two ions here. So we say we have a high amount of each of them ions. So imagine a beaker with both of these going on at once. Okay, so that's the first difficult bit, right, to get your head around. So this is where we're going to throw a little bit of a curveball into it. This is where it gets a little bit complicated. Just constantly keep in mind them two reactions at once. They're both in the same beaker, and this will help. So what happens when we add an acid to this buffer? An acid's H+, remember. So the H+ ions will react with the CH3 COO- ions in solution. Yeah. Why do they do that? Because positives will react with negative ions. Yeah. And we do have CH3 COO- ions. We've got them here. So thankfully, we've got an abundance of them as well. We've got loads of them here. We've got a salt that produced loads of these ions, so that's fine. So we can add loads of H+ ions, and there's loads of COO- ions in there. So what that means, this is where it gets a little bit complicated, so we've now got to interlink these two equations together because they're happening in the beaker at once. Remember what I said? So you've got more CH3, so you've got more CH3 COOH is produced, which means equilibrium shifts to the left. Okay, so we are producing, the H+ is reacting with this, so what we're producing is more of this. So by default, we're shifting it to the left because this bit, when we write them above each other, is to the left of that. We are moving that arrow's pointing left, isn't it? Okay. What happens when we add a base to this buffer? So have a think. OH-, the minus is going to be attracted to a positive ion, isn't it? Something that's positive. So in this case, it's going to be attracted to this, which is H+. Now, you might think, why wouldn't it go with sodium? It will react with sodium, but it will form sodium hydroxide, which is NaOH. That is dissolved very readily, okay, in water. So you'll just go back to square one. You'll just produce Na+ and OH-. So it will react, it just won't hold for very long. It will break down straight away. The moment it's formed, it'll just break down back into it again. So what we're concentrating on here is H+ ions. Now you might think, well, there's not much of these. There's a low amount of these, so I would only have to add a handful of them in and it's already going to be overwhelmed. Well, this is where it gets quite clever. So they react with the H+ ions, but there is a low concentration of these, but they can be reproduced. This is where Le Chatelier comes in. So the OH- reacts with the H+, removes them, but this reaction is not just going to sit there and think, oh, well, I'll just leave that. What it's going to do is I'm going to replace them. You've removed some of the H+ ions from the solution. So the acid is going to break down and form more H+ ions.